Good evening, students. Continuing with our lecture on the chapter Fundamentals of Organic Chemistry. In today's lesson, we'll study about the different types of bond cleavage, attacking reagents and their different types, Huckel's rule, and aromaticity.
आज के लेसन का पहला टॉपिक है क्लीवेज ऑफ केमिकल बॉन्ड्स. As we know that in any chemical reaction, reactants they give us products. And during this process, what happens? The old bonds in the reactants are broken down to form new bonds, which gives rise to products. So if we consider any general chemical reaction where the reactant AB gives us a product CD. So what will happen? This process will involve breaking of this chemical bond and formation of this new chemical bond. Now, this breaking of this chemical bond totally depends on what is the electronegativity of these two atoms, whether the electronegativities are same for A and B or they are different. Electronegativity, as we know, is defined as the tendency of an atom to attract the shared pair of electron towards itself. So about electronegativity we have studied in details in the chapter called chemical bonding. So electronegativity difference की वजह से कोई भी बॉन्ड या तो पोलर हो सकता है या नॉन पोलर हो सकता है. कैसे? जैसा कि हम जानते हैं इलेक्ट्रोनेगेटिविटी को हम इस सिंबल काई से डिनोट करते हैं. सो काई फॉर ए, इफ काई ए इज इक्वल टू काई बी, that means there is no electronegativity difference between the two atoms in the reactants. So in that case, the bond between A and B, this bond will be non-polar. And this only means कि bonds के जो electron है इस A B के बीच में जो covalent bond है इनके electron they are equally distributed over A and B. But if there is an electronegativity difference between the two atoms, if chi A is not equal to chi B, then this bond is a polar covalent bond. यहाँ दो केस अराइज करता है. Either chi A may be greater than chi B or chi A may be less than chi B. अब इन्हीं कंडीशंस पर डिपेंड करता है कि एक केमिकल बॉन्ड किस तरह टूटेगा. वेदर केमिकल बॉन्ड का टाइप, फिजन का टाइप होमोलिटिक होगा या हेट्रोलिटिक होगा. ये दो तरह के क्लीवेज होते हैं कोवैलेंट बॉन्ड्स के. टोटली डिपेंड करता है इलेक्ट्रोनेगेटिविटी डिफरेंस पर. तो अभी जैसे हमने देखा काई ए मे बी इक्वल टू काई बी और काई ए may not be equal to chi b. ये दो कंडीशंस थे. अगर इलेक्ट्रोनेगेटिविटी डिफरेंस नहीं है दोनों एटम्स के बीच में, then it will lead to the cleavage of chemical bonds in such a way that the bond के जो दोनों इलेक्ट्रॉन हैं वो equally दोनों एटम्स में डिस्ट्रीब्यूट हो जाएंगे. Let us see how this happens. Suppose we have this bond AB and there is no electronegativity difference between A and B. So chi A is equal to chi B. In such a case, one of the electrons of this bond will go to B and the another one will go with A. And this gives rise to A free radical and B free radical. These two are called free radicals. So free radicals are formed during a homolytic fission of a chemical bond, and this type of fission in which the two electrons of the shared pair, that is bond, is distributed equally between the two atoms after the cleavage, this type of fission is called as homolytic fission. Now coming to the heterolytic fission, if there is an electronegativity difference between the two atoms forming the bond, that is A and B, then in that case we have, suppose in this case, in first case, the electronegativity of atom A is greater than that of B. Then in that case, both the electrons of the bond will stay with A and so it will acquire a negative charge while the other atom will acquire a positive charge. Coming to case 2, if electronegativity of atom B is higher than electronegativity of atom A, then the 2 electrons will shift towards B and the B will leave off taking the 2 electrons, and this results in the formation of a positive charge on A and a negative charge on B. This type of fission is referred to as heterolytic fission, and they lead to the formation of charged particles, cations and ions, or in other words, they lead to the formation of either electrophiles or nucleophiles, or they may lead to the formation of carbocations, carbon ions. We will study about them in details in our coming topics. So these are the 2 types of cleavage that a covalent bond may undergo.
अब हम देखेंगे अटैकिंग रिएजेंट्स क्या होते हैं. किसी भी ऑर्गेनिक रिएक्शन में किसी भी ऑर्गेनिक रिएक्शन को हम इस जनरल फॉर्म में रिप्रेजेंट कर सकते हैं. सबस्ट्रेट प्लस रिएजेंट gives an intermediate which then decomposes to give us the products. Substrate मतलब उस ऑर्गेनिक कंपाउंड को हम सबस्ट्रेट कह रहे हैं जो मेन रिएक्टेंट है. रिएजेंट वो स्पीशीज़ है जो अपने साथ या तो इलेक्ट्रॉन्स लेके आ रहा है या खुद इलेक्ट्रॉन डिफिशिएंट है और इलेक्ट्रॉन्स की तलाश में है. तो ऐसे स्पीशीज़ सबस्ट्रेट के एक पर्टिकुलर सेंटर पे अटैक करेंगे और उनके साथ बॉन्ड्स बनाएंगे. ऐसा करने से they will give rise to a very reactive unstable species which is termed as an intermediate. The intermediates are so unstable that they don't stay for a long time. They have a very short lifetime and they decompose to give products. So this is how any organic reaction can be represented. अब इसमें हम इस reagent के बारे में study करेंगे. Reagent इसके लिए पहले हम एक एग्जाम्पल ले लेते हैं. सपोज देयर इज एन एल्डिहाइड और एनी कार्बोनाइल ग्रुप फॉर एग्जाम्पल, एंड वी अलाउ इट टू रिएक्ट विथ अ cyanide ion. Now cyanide ion has got a negative charge in it. As soon as we bring it close to the carbonyl compound, we know that electromeric effect will take place. So in electromeric effect, the pi bond of this carbon-oxygen double bond will shift towards oxygen atom because oxygen atom is more electronegative than carbon. So carbon atom will become electron deficient, and as soon as it becomes electron deficient and needs electron, the cyanide ion with its negative charge will attack this electron deficient carbon atom. What will happen then? We will get an unstable intermediate. The cyanide ion will get itself attached here, becomes a cyanide group on this molecule. This pi bond will become single, this double bond will become single, and oxygen will now carry a negative charge. Now this is an intermediate, a negatively charged species. This is unstable, and then whenever you bring some H plus ion close to it or you perform the reaction in acidic medium, it will immediately abstract this proton from the medium and will give rise to a product. This product that I am writing here is called as a cyanohydrin. This is a very common and simple example of nucleophilic addition reaction of carbonyl compounds. Now, if we watch this reaction closely, we will find that this was the main compound on which the attack was taking place. And who was attacking or what was attacking? The species that was attacking the electron deficient center of the substrate was the cyanide ion. So in this regard, this carbonyl compound will be regarded as the substrate. The attacking action was performed by cyanide ion, which is the negatively charged species here. It is rich in electron and it can attack any center which is electron deficient, and that is why it attacks this carbon center, because it is electron deficient. Such species will be regarded as the reagent. On the other hand, when the substrate and the reagent will react, they will give rise to an unstable intermediate, as I told you earlier that it has a very short lifetime and it decomposes immediately to give us the product. So in general, any chemical reaction can be represented by this simple picture,
That substrate plus reagent gives us an intermediate, which in turn gives us a product. And in this particular example, the carbonyl compound is acting as a substrate. This is the attacking site or the attacking center or the active center of the molecule, and cyanide ion is acting as the attacking reagent here, and it is giving rise to an intermediate, this, and the intermediate then further decomposing us to give us the product. So this is how we can understand what an attacking reagent is. Coming to the types of attacking reagents, they are basically of two types, electrophiles and nucleophiles. So electrophiles, as the name suggests, they are electron deficient species, and they will prefer to attack that center of the substrate molecule which is electron rich, so that the electrons can be accessed from that site and its electron deficiency can be reduced. Nucleophiles, on the other hand, as the name suggests, they are nucleus seekers. Nucleus, we know that nucleus is a positively charged part of the atom. So these species are basically seeking an electron deficient centers. They are seeking such centers because they are electron rich themselves. They carry either a pair of electron or a negative charge with them, and so they are capable of donating those electron pairs to some site in the substrate where there is some sort of electron deficiency. So this is the basic difference between electrophiles and nucleophiles, that electrophiles are electron deficient species. They seek electron rich centers in the substrate molecule, while nucleophiles are the electron rich species and they seek the electron deficient centers in the substrate molecule. Now both of these reagents, they are of two types. Electrophiles, we'll first of all discuss what are the different types of electrophiles, and we'll see some examples of each of these two types. The first type is that the neutral electrophiles. Some electrophiles do not carry any charge, but they carry a central atom which is electron deficient. All Lewis acids are examples of such neutral electrophiles. Let us take some example. Say AlCl3, aluminium chloride. In aluminium chloride, the central atom aluminium is electron deficient. As you can see, its octet is not complete. So it can act as an electrophile because it is in need of an electron. The compound BF3, you see BF3 also is in short of an octet. In BF3, there are 3 single bonds, BF single bonds, and there are only 6 electrons in its valence shell. In boron's valence shell, there are only 6 electrons, because of which it is considered to be an electron deficient center. And hence what happens? It is capable of attacking a center in the substrate molecule which is quite electron rich, and from there it can accept some electron and become stable. So such species are neutral electrophiles. Some other examples are SO3, sulfur trioxide, and FeCl3, ferric chloride. So all these are examples of neutral species, and each of these cases the central atom is electron deficient because they have an incomplete octet configuration. Coming to the second type, that is positively charged electrophiles. In positively charged electrophiles, the central atom will carry a positive charge, and whenever there is a positive charge, it indicates electron deficiency. So a positively charged electrophile will easily attack any center or any active site of the substrate which is electron rich and can accept some electron and get bonded to it. Some examples of positively charged electrophiles are proton, that is H plus ion, hydronium ion, H3O plus, or NO2 plus ion. All these are positively charged electrophiles. Then Cl plus ion. So these are examples of positively charged electrophiles which can attack any electron at center in the substrate and can form bonds with them, thus acting as an attacking reagent. Coming to the different types of nucleophiles, again the first type is a neutral nucleophile. Neutral nucleophiles will not carry any charge, but they will carry a pair of electrons, unshared pair of electrons, or you may say they carry lone pair of electron. The central atom in such attacking reagents, they carry a lone pair of electrons. So for example, ammonia molecule. In ammonia, nitrogen atom carries a lone pair, and so this lone pair can be donated to any electron deficient center in the substrate. Thus, ammonia can act as a nucleophile with this donor atom nitrogen carrying a lone pair. Similarly, water molecule. In water molecule, you can see oxygen atom carries two lone pairs, so it acts as a nucleophile. So, water molecule can also be regarded as a neutral nucleophile, carries no charge, but the central atom carries two lone pair which can be donated to the active site which is electron deficient in the substrate. Similarly, alcohol molecules can also act as neutral nucleophiles because the central atom oxygen carries a lone pair of electron. Coming to the second type of nucleophiles, they are negatively charged nucleophiles. As the name suggests, these nucleophiles will carry a negative charge because due to some sort of heterolytic fission taking place in some compound, they might have carried both the shared pair of electrons with themselves, and thus they have become negatively charged. Say for example, OH minus ion, hydroxide ion. Hydroxide ion is a very good example of nucleophile. It carries a negative charge and it can attach itself to any electron deficient center in the substrate molecule. Similarly, halide ions, which can be F minus, Cl minus, Br minus, I minus, all of them act as nucleophiles. Similarly, alkoxide ion. Alkoxide ion is formed by the cleavage of this bond in ethers, OR bond in ethers, when both the electrons of the shared pair goes with oxygen atom and it carries a negative charge. So, this is how alkoxide ion is generated, and alkoxide ion can act as a good nucleophile because it carries a negative charge. Similarly, cyanide ion. Cyanide ion carries a negative charge, and so it can be regarded as a negatively charged nucleophile. So, these are the two types of attacking reagents, electrophiles and nucleophiles, and they have their different types and some examples of them. Coming to the next topic of Huckel's rule. In this, we will try to understand what are the rules that makes some compounds aromatic and some compounds non-aromatic or not aromatic. So, Huckel's rule is a rule that states that all those compounds which are planar, conjugated and have ring system in them, also have delocalized 4n plus 2 pi electrons, all these compounds will be regarded as aromatic compounds. So, the three main criteria for any compound to be aromatic according to Huckel's rule are: it should be planar, that means it should be flat, lying on the same plane, all the atoms should be lying on the same plane. Secondly, it should be conjugated, that means alternate double and single bonds or alternate pi bonds and lone pairs should be there in the system. And thirdly, there should be 4n plus 2 number of pi electrons in the system, and that should be delocalized in the form of a cyclic ring. Also, one more thing we have to keep in mind here, that here the value of n is some whole number, that is 0, 1, 2, 3 and so on. So, let us try to understand how Huckel's rule can explain the aromaticity or aromatic character in some compounds. The first compound that was discovered to be aromatic was benzene. It's the simplest aromatic compound, and as you can see here, the structure of benzene is this. It has 3 pi bonds in its ring, and these pi electrons of the bonds are delocalized, and so most of the time we write the resonance hybrid of benzene as this, and this we have already discussed in resonance. Now, in benzene, as you can see, there are how many pi bonds? Total number of pi bonds is 3. That means total number of pi electrons is 6, because each bond is composed of 2 pi electrons, and so we have 6 pi electrons in benzene ring. Now, equating this value of number of pi electrons with 4n plus 2, as the rule is also termed as 4n plus 2, because of this 4n plus 2 is equal to 6, because if we want to know whether the system has 4n plus 2 number of pi electrons or not, we have to equate it with the total number of pi electrons. So, the value of n comes out to be 1, and which fits into the Huckel's rule, because according to the conditions of Huckel's rule, any system having 4n plus 2, any planar and conjugated ring system having delocalized 4n plus 2 pi electrons is considered to be aromatic, provided the value of n should be a whole number. So this indicates that benzene is an aromatic compound. There are more such compounds like benzene which can be regarded as aromatic, and they also contain benzene ring in their structures. So for example, naphthalene, anthracene and phenanthrene. All these compounds, they are known as benzenoid compounds. Why benzenoid compounds? Because they have benzene ring in their structures. So all those compounds which have benzene rings in their structure, they are regarded as benzenoid compounds. And so just like benzene, all such compounds, all such benzenoid compounds will be aromatic in nature. Let us see these cases where whether naphthalene, anthracene and phenanthrene satisfies Huckel's rule of aromaticity or not. As you can see in naphthalene, there are 5 pi bonds. There are 5 pi bonds in naphthalene, and so that means there will be 10 pi electrons. 10 pi electrons to be equated with the 4n plus 2. That's the formula. So the value of n here comes out to be 2. Again, it is a whole number. That means Huckel's rule is satisfied here, and so naphthalene is aromatic. Similarly, we have anthracene. There are 7 pi bonds in anthracene, and that corresponds to 14 pi electrons in the system. That means 4n plus 2 will be equal to 14, and from here the value of n comes out to be 3. Again, it is a whole number value, and this fits into the Huckel's rule. We have to see the other conditions also, like whether naphthalene, anthracene and all these compounds, they are planar or not. And benzene also. Benzene was planar. We know that in benzene all the 6 atoms lie on the same plane, and it is a conjugated system because all these have alternate double and single bonds. So they are conjugated as well, and these pi electrons, they are delocalized over the ring, above and below the plane of the ring, and so all the 3 conditions are satisfied in Huckel's rule. That's why anthracene is also aromatic. Coming to phenanthrene, phenanthrene is similar to anthracene. It's an isomer of anthracene, so it also has the same calculation as in case of anthracene. 7 pi bonds, 14 pi electrons, 4n plus 2 equating to 14. So n, the value of n comes out to be a whole number, that's 3. Hence phenanthrene can also be regarded as an aromatic compound. So you have to keep in mind while studying Huckel's rule, and to decide whether a particular compound is aromatic or not, not only should it have 4n plus 2 pi electrons, it should be planar, and it should be cyclic, and it should be conjugated, and all these 4n plus 2 pi electrons must be delocalized over and above and below the ring. So that is Huckel's rule of aromaticity and benzenoid aromatic compounds. Coming to some more examples now, in case where the structure doesn't contain any benzene ring, still they are aromatic. These are some of the examples like pyridine, furan, cyclopentadienyl ion, cyclopropenyl cation. All these systems, you can see, they do not have benzene rings in their structures, but they are aromatic. Let us see how they are aromatic, whether they satisfy Huckel's rule or not. Any compound we have to keep in mind which satisfies Huckel's rule, all the conditions of Huckel's rule will be regarded as aromatic, whether they have benzene ring or they do not have benzene rings. So these non-benzenoid compounds, say for example pyridine. In pyridine, in place of a carbon atom in benzene, there is a nitrogen atom, and nitrogen atom has a lone pair. Now there are 6 pi electrons, as we can clearly see, because there are 3 pi bonds in pyridine, so 6 pi electron. Again, just like benzene, it has 6 pi electrons, so 4n plus 2 equating to 6, and the value of n comes out to be 1. So one of the rules, one of the conditions is clearly satisfied, that is, it has 4n plus 2 number of pi electrons in its ring. Now the second thing, let us see whether it is planar or not. Of course it is planar because the entire molecule is flat and lying on the plane. So this is a planar, and it is also a conjugated system because it has alternate double, single, double, single, double, single bonds in it. So alternate double and single bonds constitutes conjugation. So it is a conjugated molecule. And secondly, it is cyclic as well, because we can see a ring system in this structure. So it is cyclic as well. So cyclic, planar, conjugated, plus 4 and plus 2 pi electrons, which are delocalized over the entire ring, makes pyridine aromatic. So pyridine is aromatic because it satisfies Huckel's rule, although it is a non-benzenoid aromatic compound. Same is the case with furan. In furan, there is one thing you can see, there are 2 pi bonds. Okay, so if we go by just by the face value of 2 pi electrons, two pi bonds are there, that means we feel that there are 4 pi electrons, but actually there are not 4 pi electrons, rather there are 6 pi electrons. Let us see how. The oxygen atom, the lone pair on oxygen atom enters into conjugation with these 2 pi bonds, and so we have to count these lone pairs as pi electrons because they participate in delocalization. So altogether this pi bond has 2 pi electrons, this pi bond has 2 pi electrons, and the third set of pi electron will come from the lone pair of oxygen atom. So altogether there will be 6 pi electrons in furan. So again, if there are 6 pi electrons, the situation will be similar as pyridine, and so the value of N will come out to be 1. Furan is clearly a cyclic compound. It is planar molecule, and it has a ring structure, and also it has 4 and plus 2 pi electrons, completely satisfying the Huckel's rule. Thus furan is also aromatic. There are some aromatic ions also, which can behave as aromatic, like cyclopentadienyl ion. In cyclopentadienyl ion, just as in furan, the lone pair was involved in conjugation. Here the negative charge is involved in conjugation with these 2 pi electrons, these 2 set of pi electrons. So altogether we will count them as 6 pi electrons. If there are 6 pi electrons, the system is cyclic. As we can see, it has a ring in its structure. Secondly, it is conjugated because this negative charge is in alternate position to a pi bond, and this pi bond is in alternate position to this pi bond. So of course there is a conjugation in the molecule. So planar, cyclic, conjugated, as well as 4 and plus 2 pi electrons makes cyclopentadienyl ion an aromatic ion. Similar is the case with cyclopropenyl cation. As you can see, cyclopropenyl cation has a double bond and a positive charge. So total number of pi electron is 2. So if we write 4 and plus 2, this gives us 2. So the value of N comes out to be 0. Now it clearly obeys the 4 and plus 2 criteria, 4 and plus 2 pi electron criteria. But is it conjugated? Of course it is cyclic. One of the other conditions is also satisfied. It is cyclic. But is it conjugated? Because we see here only one pi bond. So there is no alternate single and double bonds in the system. How can we say it is conjugated? Cyclopropenyl cation is actually conjugated, and it participates in resonance. Because of the presence of this positive charge here, the position of the positive charge will continue to change or shift its position between the 3 vertices of this triangular shape. Say for example, this is the first structure where the positive charge is here. In the second structure, it undergoes resonance and the pi bond shifts here and the positive charge shifts here. In the third structure, the positive charge shifts here and the pi bond shifts here. So this clearly is called as resonance, about which we had studied in our previous classes. So any system which undergoes resonance is having conjugation in its structure, in its system, and the electrons, the pi electrons present in them are delocalized. So all the conditions of Huckel's rule are satisfied in cyclopropenyl cation. As you can see, it is cyclic, it is planar, it is conjugated because it shows resonance, and it also has a delocalized 4 and plus 2 pi number of electrons in its structure. Thus all these compounds that you can see, which are non-benzenoid, have aromatic character because they satisfy Huckel's rule. There are some molecules or compounds that are not aromatic because they do not obey Huckel's rule. Let us see some of them. The first one is cyclobutadiene. As you can see, cyclobutadiene has 2 pi bonds. So 2 pi bonds means it has 4 pi electrons. 4 pi electrons, equating it with 4n plus 2, we get the value of n to be equal to 1 by 2, which is a fraction. Now fractional values, fractional values of n is not allowed. So this means that 4n plus 2 rule is not satisfied in cyclobutadiene, although it has a cyclic structure, it has a ring system, and it is conjugated also, as it appears, because there are alternate double and single bonds. So the system is conjugated, definitely conjugated, but it does not satisfy the one most important criteria of Huckel's rule, that is 4n plus 2 pi electron systems are not present in cyclobutadiene. Thus, it is not aromatic. Cyclopropene, coming to the next molecule, there are 2 pi electrons in the system. So just now we had studied in case of cyclopropenyl ion, cyclopropenyl cation, 2 pi electrons means 4n plus 2 gives you 2. So the value of n comes out to be 0. So clearly this satisfies Huckel's rule, isn't it? The value of n comes out to be 0, which is a whole number. That means 4n plus 2 pi rule is satisfied. Also, cyclopropene is a cyclic molecule. It has a ring structure. But the third criteria is not fulfilled here. There is no conjugation. There is only one pi bond present. There are no charges. There are no other alternate double and single bonds here present in the molecule. So, because cyclopropene is not conjugated, so one of the conditions of Huckel's rule is not satisfied here, and thus we can say that cyclopropene is not an aromatic compound. So you see, the basic criteria of finding an aromaticity, an aromatic character in a compound is Huckel's rule should be obeyed, and not only just one of the rules of Huckel, not one of the criteria of the Huckel's rule, rather you have to keep in mind that all the 3 conditions of Huckel's rule should be satisfied. The system should be cyclic, should be planar, should have conjugation, and there should be 4n plus 2 pi electrons in the molecule. Coming to the third example, 135 hexatriene. The very first glance at this structure clearly shows that it should not be aromatic because it is not cyclic, the very first thing. So there only we can discard its aromaticity, that it is not aromatic. Also, it doesn't satisfy 4n, it will satisfy 4n plus 2 rule because there are 6 pi electrons. But when we see that a particular compound is not cyclic, we will not check for the other criteria because the very basic criteria is missing here. So 135 cyclohexatriene is not aromatic because it is an open chain compound. It is not cyclic. Coming to the fourth example, cyclooctatetraene. Tetraene because it has got 4 double bonds in the structure. So 4 double bonds mean there will be 8 pi electrons. See, some of the conditions are satisfied here. The cyclooctatetraene molecule is cyclic. It also has conjugation. So the only criteria left to be satisfied is the 4n plus 2 pi rule. So putting the value of 4n plus 2 equal to 8, equating it with 8 pi electrons, we get the value of n to be equal to 3 by 2. So this is a fractional value which is not allowed for n according to Huckel's rule. It should be a whole number value, but here it is a fractional value. So we reject the chances of cyclooctatetraene to be an aromatic compound. It is not aromatic because it doesn't satisfy the 4n plus 2 rule. Although it is conjugated, cyclic, and it is also a planar molecule, but cyclooctatetraene is not aromatic because because it doesn't have 4n plus 2 delocalized pi electrons in its system. So this was all about the 3 topics that we discussed here: the Huckel's rule of aromaticity, the different types of bond cleavage, that is homolytic and heterolytic bond fission, and the different types of attachment.